Okie. So, learning about queues. Who here has ever been in a line before, ever? Of course you have. Anyone go to Starbucks today? Were you in a line? So, you already know what we're talking about today. When you show up to a line, let's pretend for a second the cashier is over there, and there's a line of, there's a whole bunch of people here, and I show up. If I'm following the rules, where do I go? The end of the line. And then I wait, and I wait, and I wait, you know, people are getting served, eventually I get to the front of the line. Then when do I leave the queue? When I'm next, when it's my turn. There, done. You know queues, you're good to go. That's it. That's really it in terms of what a queue is. Remember that we want to distinguish the what and the how. Well, that's like the what. Okay? Obviously, how the heck do we program this? Yeah, we're going to get there. But that's all a queue is. And just like a stack is a data structure that was really handy for like backtracking, like in assignment 2, a queue is going to be a data structure that has its own strengths and weaknesses that we can use for certain things. All right, so the point of the lecture, what are queues? Well, that's done. Define a queue, kind of done. Use a queue to solve problems, all right. I'm going to warn you that the problems I'm going to show you are quite contrived, but whatever. Examine a linked implementation of a queue, and we're going to talk about the queues functions in terms of computational complexity. Now that we're familiar with computational complexity, and again, I know we've been talking about it for quite some time, but the last set of slides was a little bit more thorough on the computational complexity. Still not very rigorous or anything, but now that things are actually kind of explained better than they ever were, we've got our heads in the right place to be able to start talking about the computational complexity of these operations. So a queue, it's a collection of elements where things are added to one end, the rear, the tail, whatever, and things are removed from the other end, the front, the head, whatever. We call this first in, first out. The first one in the queue will be the first one out of the queue, type thing. Where the stack, who remembers what we called the stack?
Last in, first out.
Last in, first out. The last thing added would be the first thing off. So, remember with the stack, all the action happened at one end, the top. With the queue, it's going to be different. We've got two ends. Things are happening at the two ends. So, if we want to implement a queue, we're going to need some like in queue. This means add something to the queue. That's it. It goes to the one end of the queue. It's kind of like pushing. Remember how push was like, okay, add something to the data structure? In queue is like the queue's version of push. That's it. At any stage, raise your hand. We'll make sure everyone gets this. DQ is removing something from the queue. It comes from the front of the queue. So the other end. If that's the rear, this is the front. We in queue over there, we DQ over here. This is like the pop. But of course, this is happening at the other end. Remember in the stack, the push and the pop all happen at the one end. Now with the queue, we've got like our in queue, which is kind of like push, and our DQ, which is kind of like pop, happening at different ends. We might want to be able to like look at the first thing in the queue. This would be kind of like peek in the stack. Look at it, don't remove it from the queue, but just have a look at it, make sure, check it out. It's like the cashier's like, who's next? Okay, you're next. All right, but I'm still working with the previous person or something. Out. Just check the front, kind of like peek. Get the size, how many things are in the queue, seems reasonable. And we might want to ask if the queue is empty. And the rule, just like with the stack, we are not allowed to access things from the queue that are not, the action's happening at the two ends. The rule of a standard old queue is the action's happening at the two ends. You're not allowed to add, insert things in the middle. There are other types of data structures, even other types of queues, that we will briefly talk about, where we are allowed to do that. But the standard, simple old queue, the action's happening at the two ends, nothing in between. We're not allowed to access those things. Just like with the stack. people were asking, yeah, but what's stopping me from accessing the third thing down? Why can't I do that? Because that's not the stack. You could do that, sure, great. You can program it however you want, but that's not following the definition of a stack. Why? Because that's how the stack's defined. Why? Because someone somewhere said that's the stack. And that's the rule. Same with the queue, yeah.
And that includes like looking at it, right? Like you don't know what's in there.
So, in terms of what you can ask the queue to do. Now, later on I'll show you an example of the queue itself is the thing following its rules. Okay, so the queue, what are the rules I have to follow? Like, what are the things I can do to interact with this queue? In queue, DQ, first, size is empty, that's it. Right, that's it. Those are the rules. If I've got a queue, if I wanted, I could, if I have 5 things in that queue, and I wanted to look at all 5 of those things, I could DQ 5 things. And be like, okay, 1, 2, 3, 4, 5, and go, oh, okay. And then I can put the 5 things back in the queue, and it's kind of starts and ends in the same state. So I'm allowed to do whatever I want with that queue, just like I can do anything I want with my stack. I can pop everything off the stack and push them back on if I wanted. But the stack itself, you can never ask a stack, give me something in the middle. You can never ask the basic queue, give me something in the middle. That's against the rules. You as the user of the queue, you absolutely could be like, I want the middle thing, there's 5 things in there, so I'm going to remove 2 things, look at the next one, and that's 2. You can do that. But the queue itself, all we were doing in queue, DQ, first, is empty socks. That's it. Great question though. Because it is important to emphasize the difference. How the thing is defined, and I can do whatever I want with the rules that I'm following with how the thing is defined. Good question. Here's queue, stick people. Someone wants to enter, they go there if they're following the rules. Delete from the front. Great. I hope that visualization helped. So, real life examples. Whoever's been in a checkout line. Have you ever been in a car at a stoplight? Of course you have. Who goes first? Person at the back?
Yes.
Hopefully not. How a keyboard works, right? So there's like a buffer, right? If I want to start entering things into the computer, and I say ABCDEFG, ABCDEFG will go into like a buffer, and then will go into like the computer to be processed one at a time in order in which they were added. So buffers are great examples of queues, printer queues, GUI events, kind of like the keyboard input. Anything where we want to follow a first in, first out rule. Anything where that like order matters, I guess. We want to preserve, okay, you're first, you're second, keep track of it that way. So, I warned you, these are kind of contrived examples. Bear with me. If I wanted, I could use a queue to do a quick little simulation example. So, I want to optimize the flow of traffic through a big city in some sort of simulation. Maybe a queue might be handy here. Or how many checkout lanes would be optimal to have open to, optimize throughput. Right? I don't want to have, like if there's not enough customers, and the amount of time each customer takes at the checkout line isn't that long, well then I don't want to employ like 10 people working at checkout because I'm paying them, they're not going to be working too much. But I want to make sure I'm employing enough that people are moving quickly, right? So I want to do that, yeah.
This might be like a very specific question, but if you were like NQing and DQing like at a rate where like they're equal, so like things are just going in and going out at the same time, and there's nothing in the queue to start with, do you really like have a queue at all, or is it just like?
Well, it's a queue, but it's empty. Actually, you bring up an interesting concept in computer science in general, is where you can have this like thing, this object, exist, but it could be empty. So for example, this is going to come up a lot more like later in computer science in your degrees. So don't worry about it too much, but there is such thing, I guess I won't draw it, but I'll commit to erasing this either way. There's a difference between like, let's say I have a function that takes a string. If I pass it null, that's different than passing it the string, like open quote, close quote, where there's nothing in there. Because open quote, closed quote, if I said like string A equals open quote, close quote, right? A is a string, but it's empty. Like, what's its length? It's 0. There's nothing there. And that's different than null. Null is nothing. But the empty string is a string, but it's empty. Kind of like to your queue question, right? Like, oh, you know, if it's like the empty queue, is it even really a queue? Well, it's a queue, it's just empty, right? Now, I know what you mean. If I start to try to dequeue things from a queue that's empty, well, what do we do? Maybe something kind of like with a stack, where if we try to pop it from an empty stack, we have like an exception. We will do that. But it is important to note that something that is like empty is not null. It's just an empty version of that thing. Yeah?
Let's say you had like a queue that was like big, like, I don't know, 100 things in the queue. And would it be more efficient, or would it be the same efficiency if you were to, like, instead of running one queue with 100 things and then break it up into like 5 queues of 20?
Let's talk about that later, because we will talk about stuff like that later. Yeah. Other questions? Lay them on me. They're fun to answer. If you think of any. Yes?
Just a weird question. Can you have queues of queues?
Why not? You can have queues of queues of pointers to queues to pointers to stacks of queues. I mean, don't, but you could. If you needed to, do it. But yeah, you could have queues of queues. In fact, I used to love, back when I was teaching at Western, I used to love one of my questions on the final exam was like a queue of queues. No, the midterm had like stacks of stacks, which was weird, but I did it. And then the final had queues of queues. And it was like, well, how do you iterate through all these things? Yeah, whatever. So, yes, you could. There's nothing stopping you. It wasn't a weird question. That's a great question. Remember, computers, like, in fact, you asked a question. I love those types of questions because that shows me that you've got the computer science hat on the right way. Here are the rules. Could I do this? Yeah. Just follow. What do the rules say? A good computer scientist be like, here's my system. Here are my set of rules. What can I do? What fun can I do with these rules, right? What can I exploit? Can I have queues of queues? That's weird. Yeah, we can do it. So I like the way you're thinking. All right. So let's do this. Who here's been to Atlantic Superstore? Of course you have. So let's assume each customer is arriving once every 15 seconds. It's really busy. Everyone's stocking up, I guess. And it takes, on average, 2 minutes to process one customer. Seems reasonable, right? On average, some people a little longer, some people less, whatever. But that's how long it takes. So if this is our scenario, what I've got is I can use like a queue to kind of simulate this, set like a timer, be like, okay, one person enters every 15 seconds, how long does it take to process each person? And I can do all these calculations to figure out what the optimal number of cashiers are. So if I have one cashier, the average time it'll take over however long the simulation was 5,317 seconds doing the simulation. But of course, as I add more cashiers, the average time is going to go down quite a bit. When you look at this, what would be like the optimal number of cashiers, assuming that, I suppose, the right question to ask is like, well, how much does it cost? How much is each spending, and how much does it cost to pay a cashier? But let's ignore that for a second. They're breaking even, I guess. How many cashiers would you want to maximize throughput?
8.
Why?
Because we are getting the same.
Because it's faster. But why not 9?
It is the same.
Well, because we didn't gain anything. In fact, why would you say it's like 120? Any idea why it'd be 120 seconds?
That's 2 minutes.
That's 2 minutes. Good, you can do basic math. Good. Because that's 2 minutes. Each person takes 2 minutes. So how long does each person have to wait at checkout? Well, the best you can do is 2 minutes because that's the average time it takes each person. Great. Cool. Fantastic. Yeah?
So does the time always stabilize?
Say that again?
Does the independent data always stabilize like that? Like where it goes from really high down to...
Well, I mean, it depends. There's too many variables to account to really say for certain, but I have a feeling with what you're asking, the answer is yes. But I mean, let's be clear that there's like conditions and asterisks tied to that, right? With a simulation like this, where it's like, what's the optimal number? We might expect something like this. I mean, this is basically going like 120 is the limit, the lower limit. We can't do any better than that. So it's like, well, how's it going?
Okay.
Other questions? Are we good? Cool. So a cipher. The Caesar cipher. Who here is familiar with this idea? A couple people. So this is like a very simple way to encode a message, right? If I have the message, hello, I think I might actually just have the example here. What I'm going to do is I'm going to pick a letter K, all right? And what I'll do is if I have a string like hello, or what's that classic string everyone uses, like the quick brown fox jumped over the lazy dog or something like that? It's got like all the letters. Whatever. If I've got this string and I want to encode it so none of you can read it, what I'll do, as a simple rule, is I will just shift each character down by K. So if I have A, I'm going to shift down by 5. So A, B, C, D, E, F. All my A's will become F's. All my B's will become what? G. All my C's will become?
H.
Any idea what like my Z's would become?
E.
Z, A, B, C, D, E. Good. We'll just loop back. I know they're working up there right now. What do they do? All right, anyways. We'll just loop back. In fact, keep that looping back thing in your mind for probably not today. We'll probably get to it on Friday. But we'll loop back. We know, I mean, the alphabet's linear, right? A, B, C. What comes after B, C? What comes after C? Like, there's an answer to that question. What comes before? You can only move through the alphabet like this way. Then once you get to the end, we're out. But let's just pretend we can go back to the beginning. Like it just goes on forever. A, B, C, D, E, F, G, H, I, J, K, L, M, N, P, Q, R, S, T, U, V, W, X, Y, Z, A, B, C, D, and so on. It just keeps going on forever and ever. We'll just pretend it's like a circle. Anyways. So this is our rule. This is our cipher. Anyone know why it's called the Caesar cipher? I guess so, yeah. The legend goes, this is how he encoded his messages to his generals and whatnot. I think he used like a K of 3. I don't know. If you had to pick a K, which K would you pick? 1? Why? Because it's easy. But you want to encode it good, right? I suppose once you know that it's a Caesar cipher, it doesn't even really matter what K is, right? Because 1 will be the easiest for you to encode. But I mean, if you're decoding it and you really want to decode that message, it doesn't matter if it's 1 or... What's the biggest K you could get? 26? 25? 12? 13? Well, what do we think? What do you think? Plus or minus 30? Yeah, there you go. Why? Because once you go 14, really that's like just 12 the other way. Right? Anyways, the point is, once you know it's a Caesar cipher, all you have to do, okay, let's say you had to decode it. And here's a quick little computational complexity little quiz for you. If I had a string of size n, its length is n. Pay attention, this is important. If I have a string of size n, and it's been encoded, and you want to decode it, but you don't know what k is, what is the computational complexity of brute forcing it to the point that you know you will have the decoding? It's a really easy answer. Take your time. Talk about it to each other. Take a minute. Try to convince each other that you're right. Do it. Convince each other. You have a string of size n. Okay? And you want to decode that whole string. You know it's a Caesar cipher, but you don't know what k is. But you know that k is like a number. How long would it take you, worst case scenario, to be able to decode it? Try to figure it out. Talk about it. Don't just need your answer. Really think about it. Okay, what do we think? Raise your hand if you think you know the answer. Quick poll. Okay, keep it up, keep it up. If you think you know the answer. Okay, I want to see, who do I want to ask? Is your hand up or is it half up?
Yes. I think I know it.
What do you think?
I think it's a nested for loop where you have the outside for loop running.
Hold on. Okay, hold on. So this is the code. Oh no. Oh, that's right. So you've got a nested for loop. So for what to what?
From k from 0 to 25. Or I guess less than 26.
Whatever. Edge case.
And then the inside for loop would be I from 0 to n.
To 2n. Why?
0 to n.
Oh, 0 to n.
No.
To n. Looks. That is what the code would be. But what's the complexity of that? N squared. Who says n squared? You're wrong. Why is it n? This is n. When n gets bigger, does this part grow? The n bit. When n grows, does 25 get bigger?
No.
This is constant. So we're doing n things how many times? 25. But of course, that's 25. It's constant. It's like a 1. At the end of the day, it's only order n. Not bad. You're not going to do better than that with a string of size n if you got to go through each character. I mean, maybe we can have our program looking for like, okay, does this string make any sense, and then maybe stop early. But at the end of the day, worst case scenario, it's just going to be order n. Because the point I'm making here is, this might seem like kind of a pain, but really at the end of the day, that's not that much work. An order n algorithm, that's as good as it gets for something like this. It's pretty cool. So even though you're thinking, oh, decoding, let me put it this way. Do you think this is a good way to encode something? If you really want your secrets kept?
No.
Probably not, because it's not going to take very long to decode it. Hell, you get 25, 26 people, and you give each of them, okay, you're doing 1, you're doing 2, you're doing 3. It's no time enough, right? Anyways, order n. So let's make this better. I don't know what that's encoding, but I've got a secret message there for you.
Is it, I love CS?
Is it? I don't know.
I don't know, I just guessed.
I love CS. Okay, 5. What's 5 before? The fact that this is a capital and this is capitals, I think you might be right.
Like, what else would you say?
I don't know. I do love CS, don't you? Of course you do. So here's what we're going to do. This cipher, it's not that hard to break. Let's make it better. We're going to use a Q to just very easily, simply make this better. I have a string of size n. I don't know how big it is. I don't know if it's a multiple of any certain number. It's just some arbitrarily large number of characters. It's a really long one. Someone wrote very detailed instructions on how to invade the enemy. I don't know. And I want to encode it. But I know that the enemies, they've got their spies set up, and they know the trick. They got you, and they got the algorithm out of you, I guess. So they know the trick. It's not good. So we need to beef up our encoding. So here's what we're going to do. We're not going to just pick one K. All right? Because if I know the K and you know the K, I know the K, I encode it, I give it to you, you know the K, you can decode it. Right? But here's what we're going to do. We're not going to just have one K. We're going to have a bunch of Ks. And we're going to put it in those Ks. Each K, maybe we'll have 1, 7, 14, 2, 4, whatever. I'm going to put them in a queue. Okay? So here I've got 3, 1, 7, 4, 2, 5. Why? Because arbitrary. Those are my Ks. 1, 2, 3, 4, 5. Why 6? Because. I could have made it longer. Doesn't really matter. Point is, I've got some number of Ks. I can make it more like complicated if I increase the Ks. Whatever. Now, this would mean I will shift the first character by 3, the next character by 1, the next character by 7, the next by 4, the next by 2. Who wants to guess what the next will be? But then what do I shift the next character? 3. And then 1, and then 7, and then 4, and then 2, and then 5, and then 3, and then 1, and so on, and so on, and so on. It's going to do that looping thing. And we've got a really easy way to do this looping thing. All I will do is, let's pretend for a second the top thing is, so I've got an encoded message. And I want to decode it here, I guess. Knowledge is power. Okay, great. That's the message. So let's say I'm encoding for simplicity. That's the message. I'll go up. I'll take the first character, and then I'm going to dequeue from my queue the key. Apply the encoding. Where do I put that key? I add it, I in-queue it. It goes to the end of the queue. So things are in the queue, they get dequeued, they get dealt with, and they just get put back in the queue. So they just keep like looping through, and the queue is perfect for this. This is a perfect use of a queue. So K gets decoded with 3 and 1, O 7, and so on and so on and so on. It just keeps going. Isn't that cool? Now, here's a quick one. How long would it take to decode this message? A long time. Well, it's probably going to be worse than the other one. So here's the thing. Take a minute, talk amongst yourselves, real quick. See if you can kind of figure out the algorithm or what the complexity is. I like what you did last time. You kind of came up with the algorithm. It's like, oh, it's like 2 for loops. That's good. See if you can kind of come up with how that would have to work for this one. Go, do it. Talk, chat. Do we have any ideas? What do you think?
Well, you have to have one loop that is dequeuing and requeuing.
Dequeuing,
Like
requeuing.
dequeuing like the key with all the
Well, here, I suppose, hold on. Suppose we've got a bit of a, I don't know how many keys there are. Right? For all I know, let's say I have a string of size, okay, n. Technically, the number of unique keys I have might be bigger than n. Right? Like, what if my string is hello, but my queue of k's is 20 keys long? Right? What if I've got my key, my k, and I've got hello, And my keys are 1, 7, 12, 4, 13, 7, 2, 1. Long story short, I don't even know if the keys are going to repeat. You may have thought, oh, okay, there's repeating, that might save me some time. Technically, you don't know, right? Throws it off. Sorry, does that change what you're thinking?
Well, now, I don't know.
Now you just don't know what's going on.
Well, like, if there are that many options, wouldn't it take years then? Like, because there's so many different keys, it would take literal, like, okay, it would take a long time. I don't know.
Let me put it this way. Sometimes we can get bogged down by these algorithms. I suppose if I have the string n, so let's say I've got, I'm just going to call it like C1, C2, C3, Cn. C1, C2, C3, Cn, right? I suppose what I could do is start with 1, 1, 1, 1, and check it. How long does that take? N. Okay, interesting. So like what? That's going to be 10. But then after I check this, what should I check? 2. 1, 1, 1, 1. Then what? 3. 1, 1, 1. How much work is that?
N factorial.
N factorial? What are you thinking? What do you think?
Would be n cubed.
N cubed? Why n cubed?
Like it has to do every like it has to go all of them one, and eventually like for each one of those it needs to check all of them.
N raised to n.
What? Whoa. We're getting a lot of different numbers here. What did you say? N to the power of n. Oh, I hope not. What did you say
I
now?
have the same answer.
N to the power of n. Oh.
NC,
What? Say it?
NCK, I mean, computational
N,
C,
C,
K,
K.
a subscript.
Oh, okay.
You have N things and you are choosing K.
Okay, yeah. 25 to the end? Yikes. 25 to the end, that's it. No. What do we think here? I definitely didn't really want to spend that much time on this, but it's kind of fun, isn't it? Look, computer science is fun. Yeah?
Well, if it's just one operation that's happening a lot of times, wouldn't it just be n?
I think it's N.
Like, if you think about it, where it's just 1, 1, 1 repeating, and then 2, 1, 1, 1 repeating, 3, and then once it reaches its max, the next one becomes whatever max, 2, 1, 1, 1, etc., etc. Wouldn't that just be 1 zero?
What do you think?
N into n factorial.
N?
Into n factorial.
N what?
Multiply by n factorial.
Times N factorial? That's so bad. Oh. What would the algorithm, okay, so I just kind of showed you that. What would the algorithm look like? So here's the thing. For each character, I have to, look, yeah, we're going to have a bunch of those. For each character, I need to check 25 things, right? But I have n characters, and it takes n to go through it. Ooh. I wonder if it's as bad as you think. You know what? We'll stop. What do you think?
Well, I'm thinking it's like if you were trying to guess a bank code, you would need like 0000 and then 0001
Yeah.
So when you have to just check 25 things n times, but n times, so like 25 n squared.
So you think n squared?
25 square.
I don't know what I think.
We're going to leave this part here, and let's see homework worth nothing but bragging rights. On Friday, I want to see if you can come up with your answer. But no more of what we've just been doing, like, is it n squared, n factorial, n to the n? No more of that. I want you to come up with an answer and have like a nice, like, proof. It doesn't have to be that rigorous or formal, but some sort of like demonstration. Like when you tell me on Friday, I'm going to ask you why, and it needs to make sense to me. Yeah.
If you're checking every, I guess, possible answer for the one element, how do you know you're right?
Because when I decode it, I go like, can I read it?
But like if you're doing one element at a time.
Well, I would go, okay. I check 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and then I read it, and go like, did that make sense? Okay, I'll 2, 1, 1, 1, 1, 1, 1, 1, 1, 1. Did that make sense? Okay. 3, 1, 1, 1, and so on. Da, 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 da. You might come up. I don't want to say anymore. All right. Let's talk about Qs, which we're supposed to be talking about. All right, so Q implementation. So we know what a Q is. We've got that down pretty good. Now we need to know how we're going to actually implement this thing. So remember, the implementation, like the what and the how, they're different. What is a Q? Well, in Q, DQ, that's how it works. How is it implemented? We'll look at one implementation, but what do we need? We're going to need some sort of container. So last time when we did the stacks, we did an array stack and a link stack. How about this time with the Q? Let's start with the linked version, right? Let's start with a linked stack, or pardon me, a linked Q, and then later we'll do an array Q. But forget arrays right now, we're doing the linked version. So there we go. We need something to keep track of the front, pointer, the rear, another pointer, the size, an integer, that's easy. So you have something like this. I'm going to want a structure that looks something like this. Front is a pointer to a node that is the front of the queue. Rear is a pointer to the last thing in the queue. Count, it's just the count. Great. If I add something, what should happen to count? Go up. If I remove something, what should happen to count? Goes down. Great. If I look at the front but don't remove it, what should happen to count? Good. So if I enqueue something, this is what it'll look like. What changed here when I enqueued? The count changed, but what else changed?
Rear pointed to.
Rear.
Rear.
The front stayed the same. Rear just updated to what it was pointing to. Not too bad. If I remove something, where did it get removed from? The front. What updated? The count. What else?
Friend.
Say the front. The front, there you go. But of course we have edge cases, right? What if this queue is empty? First of all, think, what would this look like if there was nothing in this queue? What would the count be? Good. What would the rear point to? I guess nothing, like null. Null point. What would the front point to? Did I just ask that? What would the other one point to? Nothing, yeah, I guess nothing. Huh. So if the queue is empty, front and rear will be pointing to nothing. That's important. Yeah.
Is there like two separate null pointers that are in front of a pointer, or are they point at the same?
They're just going to be pointing to the same special value that means it's pointing to nothing. Yeah. Yeah.
So each node, if I'm looking at it right, does the pointer point to the node that's behind it in the queue? Like what's?
Yeah. So front, the thing that would come after, this is the guy that just entered. This is the person that's ready to get taken out. And of course, I drew these as pointers to these squares. I mean, really, I can make this generic. We will. And these can hold on to really anything that we want, but whatever. So, what if the queue only has one thing? What's the front point to? The one thing. What's the rear point to? the one thing. The front and the rear are the same. So we actually have these two special cases. Okay, the general case is, I guess, going to look something like this, right? But then it might just happen that the queue is empty and front and rear are pointing to nothing. Or the queue only has one thing and the front and the rear are pointing to the same thing. We should keep that in mind for our implementation because that might be important. So, our linked queue header. This is, of course, going to be the first bit of the header, the part of the header that we were used to, but we are going to make it generic, which means where are we actually going to write all the code?
Header.
In the header, but like down here. Right. What's the CPP file going to look like? Like nothing. It's going to be like include. That's it. Cool. So, okay, I add that because we're going to need nodes. Okay. It's going to be generic. We like that. Count a node of type T, pointer, front. A node of type T, pointer, rear. So far, so good? That's it. Those are the attributes. That's it. Each queue only needs to know these three things. And you might think, well, hold on, but that queue has a whole bunch of things. The queue only needs to know where the front is and where the rear is. Because if I'm the queue and I know where the front is, I could get to the thing after that, and then the thing after that, and the thing after that if it exists. But all I really need are these three things, which is pretty cool.
What about the data in there? There is nothing.
Well, that's dealt with by the node. So great question. The nodes are a separate object. It's a generic node. When we enqueue, dequeue, we'll see where the nodes come up. But the point is, the data isn't stored in the queue really, it's stored in the node, which is like in the queue. Yeah. Yeah?
So the last element in the node will be still pointing to the null point?
Yes. Yeah. So rear will point to the last thing, but that last thing's next will still be like null point.
Oh.
Yeah. Other questions? Cool. So we've got our constructors, copy, deconstructor. Great. By the way, a lot of people on the midterm, just a note, the constructor and deconstructors are like functions. They're methods. Don't forget that. A lot of people did. Some people, they put push pop is empty. Some people put the constructor push pop is empty. Few people actually got it right and said constructor push pop is empty deconstructor. That was the right answer. Anyways, just be aware of that. And then we're going to need our DQ, InQ, first, size is empty. Is empty, that just tells me true or false, is it empty? Size, it's going to be easy. Return whatever the size attribute is. InQ, it's going to take something of type T that we want to add, that's the data. And DQ, all it's going to do is just return something of type T. That's all. The data. It's not returning a node, it's returning the thing of type T. All right, we'll pick up here on Friday.